Okay, good. So, last time what did we do? We did two very important things. We did the Ginzburg criterion. And that basically says that you define something which is, that object, which is basically an integral of the order parameter over some region, some volume of size, of linear size. And then what you want is you want this guy, the connected part, to be much, much less than the average of the thing itself squared. And when we applied the Ginzburg-Landau theory to this, we found that this implies this can only happen if d is bigger than 4. So for d less than 4, it doesn't happen, and that tells you, actually you can do it in a bit more sophisticated way. Okay, so you can put in all the constants here, and if you have a way of estimating what are the things, so remember I told you that r was basically some constant times t minus tc, right? If you have some idea what that constant is, okay? And if you have some idea what the other constants are that come into the Ginzburg-Landau action, you can do a little bit better than this, and you can tell how close you have to be to tc before the Ginzburg-Landau theory stops working. Okay? In fact, this was the original motivation for the Ginzburg criterion, because Ginzburg was trying to work with the superconducting transition, okay, the superconductor normal metal transition, and there he wanted to find out how close you can go and still apply mean field theory. It turns out that if you have a good metal and something like lead, and it becomes superconducting at a pretty low temperature, like I don't know, 15 Kelvin or something, or maybe just 5 Kelvin, I don't know what lead becomes superconducting at. But whatever it is, it's a pretty small temperature, and given all the constants, it turns out you have to go within 10 to the minus 4 or 10 to the minus 5 Kelvin to see the critical fluctuations. It works really well. Okay? Mean field theory works really well for ordinary metallic superconductors. Okay, now the high DC materials are very different, and there the critical region is actually a fraction of a Kelvin. So you can actually see the non-Ginzburg-Landau behavior in a high DC superconductor. Alright, so that was one thing that we did. Any questions about this? Yeah?
Could you kind of give a physical intuition of the system?
Yeah.
How would it look like if it does not obey this condition? Like suppose this condition, because this condition, irrespective of the means the criterion for the mean field theory,
This condition always is satisfied.
yeah. So
For a real phase transition, it has to be always satisfied.
so if this is not satisfied, there is not a well-defined phase in the system.
That there is no phase transition in the system if this is not well defined. That is correct. So if there is really an order parameter in one phase and not an order parameter in another phase, this cannot, this always has to be satisfied. The only question you can ask is my set of critical exponents that I believe describes this phase transition, does it satisfy this inequality? Okay, it has to. If you have a good physical set of exponents, it has to satisfy this inequality. It doesn't satisfy it for the Ginzburg-Landau set of exponents. Or it satisfies it only for d bigger than 4. Or, let me call mean field exponents. Okay? In fact, this is one of the inequalities that exponents have to satisfy. Okay? If you have a correct set of exponents, suppose you're doing some numerics, right? And you find some set of exponents. There's always going to be some error in the exponents, right? And you want to constrain it somehow. You can use this. Now it won't be exactly what I said, because I kind of used the mean fieldness of this whole thing throughout the derivation. But you can do a little bit better, and you can actually use exponents that are the correct exponents. And then it always is satisfied. Okay?
So for a system, suppose the mean field theory doesn't work.
Yeah.
So for using the mean field theory, if we check if this criteria is fulfilled, we will see that no, it's not.
Correct.
But the same criteria is fulfilled if another theory we have.
So, if you have a correct theory and some correct exponents,
Yes.
they have to satisfy this.
Okay.
Okay? All right, that's a good question. So it has to be satisfied.
Because you are giving
For the true exponents.
some physical intuition about how the phases or the different
Yeah.
phases look like.
That's
So
a
that
very
I
good
wanted
point.
to understand, like, how did we
It
come?
cannot be violated. If there is a phase transition, there's no way it can be violated.
So one region of the system cannot be in any other phase than the other region of the system.
That's right. That's right. Unless you have some kind of disorder in the system, right? I mean, you can imagine something in which you have some kind of Ising model where some bonds are strong in one region and they're weak in some other region, right? The place with the strong bonds will order first. Okay, but I'm talking about a translation invariant system,
Homogeneous system.
a homogeneous system. So there's no,
So they will have the same order parameter for all the regions.
no, the entire system orders at the same temperature. Okay? That's what has to happen.
For systems where we can't define proper order parameter like spin liquid models.
Spin liquid transitions are, let's see, you can define some kind of order. You can define some kind of topology. It won't be a local order parameter. That is true. Okay, but there are other ways of describing those transitions. Ginsburg-Landau doesn't work for those things. Ginsburg-Landau usually works for things that have an order parameter.
And what happens at D equal to 4?
E equal to 4, like I said, this mean field is correct, but there's some logarithmic corrections to mean field. It's not exactly correct, but it's pretty good.
And then one more concern, like we were talking about the higher dimensional objects like 5, 6, 5, 8 kind of a thing.
Yeah,
So I just wanted to understand the map between what people do in QFT and talk about effective field theory with these higher objects.
yeah,
Because here you have a physical cutoff, because this 2 pi by a is your
Yeah.
cutoff for the lambda. But for QFT, normal motivation is to write a dimension 4 object and call it the UV complete description. Now, these things, these higher power things come about when you integrate out the heavier scales in the full dimension 4 thing.
Yeah.
And then you get all kind of Fedora
Yeah.
lots of all height. But
Yeah.
here you are starting with something which already has everything in it.
yeah,
So how do I, there the higher powers come about after integrating out.
yeah.
Here you are starting with these higher power things already present. So, I mean, how is that like something else is happening there and this is something else?
Absolutely.
No, it's all part of the same deal, that the answer is long. It's not a short answer. Okay, so I cannot give you the answer right now. Okay, because we don't have the technology. If I give you the answer right now, it'll be about 45 minutes. And it'll involve concepts that we haven't actually covered yet. Okay, so let's wait for that. Or you can come to me and we'll talk about it. Okay? I would rather not talk about quantum field theory, okay, if I can avoid it. Because that makes it seem unnecessarily complicated. This is a lot simpler than what people normally study when they do quantum field theory. Okay?
Are
All right.
we going to do Bishes theory or the?
No, we are not going to do BCS. BCS theory is a mean field theory.
Yeah, I mean this is very complex.
Yeah, we're not going to do it. Okay, we're going to do something else that has a U1 order parameter. But it's a global U1. It won't be a gauged U1. Okay? All right? Other questions?
So in the Wilsonian RJ, you said that this U6, U8 term is relevant for D is equal to 2 dimensions, so that
They're all relevant for D equals 2. Yeah.
so these RJ consider this taking this small size and integral out will not be applicable for D is equal to 2.
No, that is also not correct. Okay? You have to be clever. So as we go on, we'll discover how to be clever
They are
about
relevant or
all these
marginal?
things.
No, higher, in equal to 2, higher powers, relevant or marginal?
It all depends on which fixed point you're talking about. So when I did the Wilsonian RG for you last time, which I'm going to just review briefly again, the starting point, right, the tree level RG, I implicitly did it around the free field fixed point. The free field fixed point. Okay? It turns out there are other fixed points. And if you're clever, you sit around one of those other fixed points, and even when you go to dimension 2, you can make 5, 4, 5, 6, everything irrelevant, except for 1. And that is in fact the theory of the Eisenhower. Okay? But these are very advanced questions. Okay, so let's focus on simple things. Alright. Any other simple questions? Not involving quantum field theory. You know, to tell you the truth, I was very put off by quantum field theory, because when I first learned quantum field theory, it was all about infinities. And it seemed completely bogus. And that way of teaching quantum field theory is really bad. In fact, it is bogus. Okay, that's the wrong way to teach quantum field theory. This is the correct way to teach quantum field theory. Okay, Wilsonian approach. Okay, but we can have the argument later. Okay, so now, Wilsonian RGs, right? So let's very briefly review what we covered. So I said first step in Wilsonian RGs is to go from something like a square Brillouin zone to something like this, where I've thrown away all kinds of information about what is the coordination number of the lattice, what is the symmetry of the lattice, because I'm assuming that by the time I come to the critical point, all the details of the lattice structure have been all wiped out. Okay? And I'll be left with something rotationally invariant. So that's what I'm assuming. Okay? For some phase transitions, that is not true. Okay? So in those cases, you have to actually retain the directionalities of the lattice. But we will not be talking about such transitions. Let's just focus on the simple cases.
Sir, I forgot that.
Yeah.
How can we approximate a Brillouin zone to a sphere with radius?
Because all the short distance details don't matter for the critical point.
Short distance?
The short distance details
Yes.
don't matter.
Okay.
So at short distances, that you know that the lattice is square.
Okay.
But as you go to long distances,
Mhm.
right, you don't actually, I mean, suppose you look at a piece of metal, you don't know whether it's a FCC lattice or a honeycomb lattice, right? So it's the same thing,
Okay.
okay? Then we said what we're going to do is we're going to successively integrate out little thin shells of this. And the parameter that characterizes this is something that I call dl. And this L will be the flow parameter of the RG. Okay? So what we want to do is we want to integrate out between lambda times 1 minus dl and lambda. Okay, so in this region, we want to integrate it out, and then we want to see what the remaining effective theory is. Okay? Good. So we said, so we start with our effective action, which is like d to the dx, 1/2 grad phi squared plus m squared over 2 phi squared plus lambda by 4 first. Then we say that we have a phi, which is a phi slow plus phi fast. The slow degrees of freedom are sitting in here. The fast degrees of freedom are sitting in that little shell. Okay? Then what we're supposed to do is we're supposed to decompose this S into 3 parts. So S will be something that depends only on the slow degrees of freedom, plus something that depends only on the fast degrees of freedom, plus some interaction. And all the back reactions of the fast and the slow are going to come from this. Okay? But before we did that, we had to actually figure out, as we did our scaling, what is it that we want to keep fixed. And this is really the question of what fixed point we want to be at. Okay? That's really the question. So, we focused on this guy here, and then we said, in this guy, I'm even going to throw away this. Okay, I'm just going to look at the quadratic term. So in the quadratic term, this S0 less, okay, 0 means quadratic. Okay, this guy looks something like integral d to the dk over 2 pi to the d times phi tilde of k, and this is less phi tilde minus k less k squared plus m squared over 2. And this goes to lambda times 1 minus c. Alright? And we decided that we're going to keep this particular coefficient fixed as we did our stage. And then what we want to do is make the theory at every stage, once we integrate out certain thin shell, we want to restate everything so that the theory looks the same as it did before. So then what we did was we said we will take another k prime, which is k times 1 plus dl, so that it restores the cutoff back to what it was, lambda. Okay? But then, in order to keep this guy fixed, we have to do something a little strange. We have to say that we're going to define this guy as 1 plus the L to the minus, what was it, b plus 2, okay, times phi tilde of k 1 plus dl, sorry, k prime 1 plus 1 minus 2. Okay, this was the scale that we had to apply. Okay, good. Given that, what happened to this term was that this s less after this rescaling went back to that, and then you had e to the k prime over 2 pi to the d, then phi tilde prime of k prime, phi tilde prime of minus k prime squared plus m squared 1 plus dl squared over 2. So the price of keeping this coefficient fixed is now this coefficient is not fixed. Okay? So this tells you that m squared, at least at this level, there's going to be more corrections to m squared. But at this level, m prime squared is going to be equal to m squared times 1 plus dl squared. Okay? That's the way m squared is going to flow, at least at this order. Okay. Now, we said given this, we can actually figure out if I put a small perturbation. So my idea now is the following. I'm going to sit at the point where all these coefficients, everything, m squared, lambda, u6, u8, everything is 0. Okay? And then I'm going to ask myself, if I put in one of these things, is it relevant or is it irrelevant? Okay? So here's the free field fixed point. Okay? It's the most trivial fixed point you can imagine. So this point has m squared equals 0, lambda equals 0, u6 equals u8 equals whatever else. Everything's 0. Okay? You agree that if I have that, it's a fixed point. Why? It's because the theory is quadratic, right? And the theory is quadratic, this interaction piece is 0. It doesn't exist. So what I have done is pretty much everything. Right? So it's very trivial that you can see that there's a fixed point. Now at this fixed point I can ask myself, how do all these different perturbations behave? Okay? So I've already done it for this. And then I did it for lambda. So how did it work for lambda? So now I'm going to do it in real space. So if you remember in real space what happened, you just take the Fourier transform of what I did in K space. So it turns out that phi prime of x is actually equal to 1 plus dl to the minus b minus 2 over 2. Okay? Times the original phi of x times 1 plus dl. Alright?
Sorry,
Yeah.
what happens to S interaction for free field theory?
For the free field theory, this term is absent, right? So the whole thing is quadratic. When it's quadratic, there is no mixing between the fast and slow degrees of freedom. Because remember, it's phi tilde of k, phi tilde minus k. So I'm making sure that when I do my cutoffs, okay, if k is here, minus k is here, right? So if k belongs to the shell, so does minus k. So there's nothing that connects the shell with the interior. For that, you need some power of phi that is not 2. Okay? That's the reason it's a fixed point. Okay? Fine? Okay. So I have this. This tells me the dimension of the field phi in real space is d minus 2 over 2. Alright, so here's how you do it. So let's do the same calculation that we already did in real space. Right? So how do we do it? So we say, alright, we have d to the dx and you have grad phi squared, right? Alright, so now we're going to do everything in terms of x prime. Right? What is this x prime? That's this guy here. This is what I would call x prime. Okay? So this says, so d to the dx, right? Now I want to write in terms of d to the dx prime, right? Sorry. Okay? So now, what I will do is I will write as d to the dx prime 1 plus dl with d. And then, am I doing this right? No, I don't think I'm doing this right. That was a minus d over 2. This will be plus. And this is plus. This will be minus. Okay, can you check your notes to see whether what I've done here is correct? Yes? This is the correct sign, right? Okay, good. So because you know that what you have to do when you do RT is expand your distance scale. Right? You shrink your momentum scale, so you have to expand your distance scale. Alright, so that is d to the dx prime, 1 plus dl to the minus d. Alright? And now there's a d by dx here. Right? X behave like 1 plus dl to the minus 1. So d by dx will behave like 1 plus dl to the plus 1. Right? So this will be minus d minus 2. Okay? Good? Times the scaling of phi. So this will now be d prime. That is still phi, right? What is phi now? Phi will be all this stuff. What is it?
Power will be a 1 negative. Phi prime
1 plus dl minus of that.
D minus 2.
It's minus?
No.
You sure? I think it has to be minus. Because I think I expressed,
Yes, that.
this is minus?
Yes.
Or is it plus? Or is the phi and the phi prime on the correct
That
side?
is plus. Large prime is plus.
That is plus. So there's a problem here. There's a problem because I want to replace phi
Just you have
in
to,
terms of phi prime.
yeah, you have to just write a relation like phi of x should be 1 plus dl will be by minus d minus 2 upon 2. Means you have to just reverse the relation. Means the relation will be like that phi prime of x into 1 plus dl should be 1 plus dl will be by minus d minus 2 upon 2 of phi x.
Sure. I can't understand it.
It's like,
Do you have the notes from before?
yeah, I had.
You had or you have? Did you copy it down correctly?
Yeah, I can copy it.
Can, but did you?
Let me see whether you have correct. Yeah, whatever you have written it is correct.
Whatever I've written is correct?
Yeah. From the last day.
Okay. No, I think, okay. So let's write it like this. Okay, so x prime is a stretched version of x. That is certainly correct. Okay, so if I want to relate the phi prime and x prime, I have to do it at a shrunken value of x. You guys agree? Okay?
This is the old X.
That is the old phi, that's right. Alright? So this sign is correct. Now that sign is also correct. So therefore, this sign will be plus. Look, I know the answer, so I know what to fix. Okay? So, but if you do it carefully, you should be able to get this without fixing anything. Okay? So you agree that this, right? So let's see. This is what I would call x. Okay? This is x, right? So d to the dx is going to be equal to d to the dx prime. You have the same problem again?
If you write it like
Should I go and write it down?
Yeah, go ahead, write it, please.
Yeah, so
What is the correct relation?
the correct thing is that means define x prime to be x into 1 plus dl.
Very good.
And then right, so let me write here, right?
Yeah.
So then the relation is like I prime of x prime, which
Yeah.
is x into 1 plus dl,
Very good.
should be the scale 1 plus dl
Yeah.
into the scale dimension, which
Yeah.
is minus of scale dimension, d minus 2 upon 2.
Minus.
Yeah.
You sure about that?
Because this is the scaling thing, and whatever the scale happen, that is like scale parameter to the power minus of scale dimension
Okay.
to be phi of x.
I think that looks right.
And then if you substitute phi x in terms of here, now in this
Okay.
action, suppose you
Good.
so
So
then
look, I'll just sit down. Why don't you do the rest of it? Okay, go ahead. Thank you. Okay, good. So we solved that problem. Okay, at least I think. Let me work it out. and
We
see
just
if it
have
actually
power
solves the
from
problem.
that, that's all.
Okay, so this thing is now minus. Right? Okay. And this is also minus. Correct?
Yeah.
Because x
is-
prime,
yes.
so x is x prime and 1 minus dr. That is also correct, right?
Yeah.
Because this is it. Okay, good. Now let us see. So start praying, okay now. So let's see if this works. Alright, so this is x. So x prime is, so if I take d to the dx, wait. So let's see what happens. So that's d to the dx prime times to the power of d over here. Okay, good. Then there's a derivative. So you know that the derivative counts opposite to the x. So this is good. Alright. Now the phi has to be written in terms of the phi prime. Right? So now there's a gradient prime. Now phi written in terms of phi prime will be phi prime times 1 plus dl to the d minus 2 over 2, whole thing squared. Okay, because this has to come over here. Now, thank goodness, it all works out. Okay? So the 1 plus dr to the d minus 2 cancels the 1 plus dr to the d minus 2. Okay? Thank you very much. Okay. Alright, good. So, we at least managed to get this in real space. Alright, now let's do it for the other interactions. Okay? Because this is a much quicker way, if you get it right, than doing the momentum space. Alright. So basically, what you got to do is just realize that every power of x, okay, so every power of x has dimension minus 1. Okay? Every derivative has dimension plus 1. Okay? Every phi has dimension d minus 2 over 2. Now you just add all those dimensions and you ask yourself what results. Okay, so now let's apply to the m squared term. Alright? So the m squared term looks like m squared integral d to the dx phi squared, right? So let's start counting. So this guy looks like m squared. Alright, now this guy will be a 1 plus dl to the minus d. Correct? Phi squared will be a 1 plus dl to the d minus 2. Okay? Good? So therefore the minus d and the plus d cancel, so this minus 2. So this tells you that in order to leave this thing invariant, n squared dimension has to be plus 2, because n squared times 1 plus d to the minus 2 has to be invariant, so n squared dimension is plus 2. So it's relevant. Anything that has a positive dimension is relevant. Okay? The coupling. Okay? Now let's look at the phi 4. So it's lambda over 4 d to the dx phi 4. Good. We do the same counting. Lambda, so 1 plus dl minus d, 1 plus dl, 2 times d minus 2. Okay. 2d minus 4. So this tells you this must be b minus 4, right? So the dimension of lambda is 4 minus d. And if d less than 4, it's relevant. Okay? Now let's look at some power, phi to the power 2n. Let's ask ourselves what happens there. Now we can do it very simply. So this is u2n to 1 plus dl to the minus d plus n times d minus 2, right? Because each power of phi is worth d minus 2 over 2. So this tells me this is un 1 plus dl to the power of n minus 1 d minus 2n. So therefore, the dimension of un or u2n, I don't know what to call it, let's call it u2n, is equal to 2n minus n minus 1 d. Okay? You can easily check that for any n, as long as you're near d equals 4. Right? So let's say n is equal to 3, right? So that will be u to the 6th, 5 to the 6th. Right? So this is 6 minus 2 times d. So anytime you're between dimensions 3 and 4, this guy is irrelevant. And the higher the power, the more and more irrelevant it's going to be. Okay? Fine? All right. Now, this is basically the complete description of the free field switch point.
So,
Yeah.
so why you are saying this positive dimension should be the relevant parameter?
Because the point is that, remember what happened over here, right? This was like the leftover part of all the scaling, right? That was this. So I'm just trying to reproduce it in a very simple way. Okay, I'm saying this guy also scales. I'm trying to figure out how it scales. Okay? The way I try to figure out how it scales is I say this entire thing must remain the same. Okay, whether I rescale it or not. Okay? In order for that to happen, since this thing scales at 1 plus dl to the minus 2, this guy has to scale like 1 plus dl to the plus 2. Okay? So it's a shortcut to figure out what the dimension is. Similarly, we also did in momentum space. Remember last time for the 5/4 coupling? So same thing, but done much faster. Okay? Good? So that's it. That's it for the free field fixed point. So the free field fixed point in, let's say, dimension 3. In dimension 3, it has two relevant couplings, that is the mass and this guy, and it has one marginal coupling, that is U6. Okay? Good. Now we want to find out what happens when we start adding interactions. Okay, so that's the interesting thing. So let's do it. a little trick. Okay, so in general, what you want to do is you want to keep as few couplings as possible, right? Because keeping other couplings makes your life hard. You want to keep very few couplings. So I don't want to deal with this U6. Okay, so what do? So I invented a little trick. Of course, I didn't do this. Okay, I'm just saying. Okay, Wilson was the one who did it.
Sir, about
Yeah.
this, for example, the spray field theory, once we have identified the relevant couplings, so
Yeah.
integrating out the higher degrees of freedom, when we have the effective field theory, but this cannot be treated perturbatively. So what do we do?
So RG is perturbation theory, but it's really perturbation theory in the high energy degrees of freedom. So when we integrate out perturbation theory, it's like integrating out everything at once. Okay, you want to calculate some physical quantity, you integrate out all the degrees of freedom and you find the physical quantity. But you can do that only as an expansion in powers of lambda or powers of something else. In RG, you don't integrate out all the degrees of freedom, you integrate out the high energy degrees of freedom. And those guys will have large denominators. If you want to think quantum mechanically, right? When you integrate out, when you do perturbation theory, there's always some denominator, right? There's some energy denominator. If you integrate out high energy degrees of freedom, the denominator will be large. And even if your coupling constant is not very small, because the denominator is large, the perturbation theory is valid. Okay? So that's the trick that's being used in RG. You'll see how it operates in a minute.
For marginal coupling, that is large, that remains large, right?
Okay, so this is marginal at tree level. Okay, so we don't know what's going to happen to it once you start doing loops. Okay? So, but I don't even want to deal with these. Okay, so what do? So this is Wilson's trick. So Wilson says that the dimension of U6, okay, what was it? We just figured it out over there. It was, okay, I have to write it out. So it's 6 minus
2b.
6 minus 2. Very good. 6 minus 2. Very good. So the claim is that as long as 3 is less than b, less than 4, U6 is irrelevant. Okay? You agree with that? So the Wilsonian trick.
Why less than that will be
Well, the upper limit is not important. But we're going to stay below 4 because above 4 mean field theory is correct. Right? So in this regime, U6 is irrelevant, right? So what Wilson says is that let me stay close. So we're going to stay close to 4. Alright? So in order to explicitly say that we are close, I'm going to define a number which is called epsilon, which is 4 minus d. I'm going to deal with small values in this. Of course, in the end, after dealing with small values, I'll put epsilon equals 1. Okay? But somehow it will give me the right answer. Okay? Magically. So, but there's a good justification for all of this. Right? The real justification is that we are talking about a particular fixed point. Okay, and at that fixed point, this U6 always remains irrelevant. This fixed point exists all the way between d equals 4 and d equals 3. At d equals 4, this guy is irrelevant. And if you continuously move with that fixed point as d decreases, U6 remains irrelevant. Okay, that's really the reason why you can treat it as irrelevant.
What do you mean when you say between 3 and 4?
Between 3 and 4. Like pi is between 3 and 4, right? So,
Yes. But how can dimension be between 3 and 4?
so when you do perturbation theory, you always introduce some artificial parameter, right? Such an artificial parameter. So, it's not a big deal. All right? Good. So, let's now start doing it. All right. So now I have thrown out U6. So I only deal with m squared and with lambda. That's all I have. Good. Now I have to take this S int seriously. Okay, so what is S int? So S int going to look like lambda over 4 integral d to the dx So that's the reason I kept this d all the time. You see, because secretly I knew that I was going to have to make it continuous. Okay, so I have to do it. Okay, good. So I have this, and then what do I have? I have 4 phi less cubed phi greater plus 6 phi less squared phi greater squared plus 4 phi less phi greater cubed. Okay? Good? So that's what I have. So now I'm going to treat this perturbative. Why can I treat it perturbative? So this comes back to your question. Okay, so the point is that this phi greater lives in this very narrow shell. So there's very little of this. In a sense, this is small because this guy lives only in a very narrow shell. That's why it's okay to do it with perturbation. Alright? So let's do it. So you have this S int. So what I really want to do now is I want to integrate over the fast fields, right? So let me write it down. So formally I will write it down like this. It's an integral over the fast fields. Okay, e to the minus S fast, right? Minus this S int. Okay, that's what I have.
Phi greater than itself can be it can be large. Why should it be small?
Sorry?
Phi greater than.
Phi greater than, the value of phi greater than can be large. But remember, what I'm doing is that it's being weighted by this. This guy has a quadratic piece that says that phi greater than, if you make it very large, then the action becomes large, and therefore that weight is suppressed. Okay, so configurations in which phi greater are very large are going to be suppressed. So it's just like the high energy decay of freedom in quantum mechanics. Its fluctuations are small. The higher the energy of something, the smaller its fluctuations. Okay?
Okay. Outside there is a phi less integral there. You are only considering only
Yeah. There's of course also this.
Oh, okay.
Yeah, but the only integral I want to do is this one.
Okay.
Right? There's also this, of course. And that also exists. But this is what I want to focus on. Okay?
Just one thing.
Yeah.
So in that S greater, there is a k square term sitting there.
Yeah.
And that k square only exists for very high momentums. That's suppressed.
It's lambda square. Yeah. That's right. That's right. I'm going to write all of it explicitly in a second. Okay? Good. So this S greater, as Ankur just pointed out, is something that looks like this. So S greater looks like integral from lambda times 1 minus dl to lambda, okay, d to the dk. And then there's a k squared, right? What is that k squared? It's really just lambda squared. Okay, times phi tilde of k, phi tilde of minus k. Right? Okay. Now,
So one thing.
Mhm.
The lambda by 4
yeah,
phi greater to the power 4, that term is also there.
that term is also there. You're right. Absolutely. This is better to write in real space, because otherwise I'll have to write a lot of integrals. Okay? So you're right. There's also 2 pi to the d. Okay? Good?
Initial I greater. The
Okay? Good. Now I believe it's correct. Okay? Good? So now what I'm going to do is I'm going to recast all of this. So remember, I'm only doing the phi greater integral. So I have a d phi greater, and then I have a e to the minus this integral, which is, integral lambda times 1 minus dl to lambda e to the dk over 2 pi to the d lambda squared plus n squared times e to the v. So this v, what is there in the v? The v has this term here, and it also has s int. Okay, that's what it has. Okay? Good? an important theorem. This is called the linked cluster theorem. Okay, it says that if I take such a quadratic action and then I average e to the anything in that quadratic action, the result of that is going to look like e to the average b in that quadratic action. So let me call it 0. Okay, plus 1/2 b squared minus b average squared plus, I don't know, 1/3 something and so on. Okay?
This theorem is the theorem that
This is called the linked cluster theorem.
This is for z by z0.
Linked cluster theorem. Okay, so the true result is this. E to the b average is equal to that. Okay? So we're just going to use this. If you want, you can do this perturbatively. You can expand things out and convince yourself that the expansion of this and the expansion of the actual average match. But the theorem is actually more powerful than that. Because you see, if you have a thermodynamically large number of variables, you're not allowed to expand it. But in fact, this theorem is true even for that case. Okay? It's a very powerful theorem. Yeah.
Just to mention that you mentioned only quadratic. But this theorem has a version which works for any theorem, not only quadratic.
But it will probably involve some more
Yeah,
stuff
some-
over here.
Exactly. So we have to write down not the connected functions, but cumulative functions.
Cumulates.
And
Exactly.
it will work exactly for any function.
But of course, you have to calculate it.
So
Not so easy. Okay, yes.
E to power v includes this lambda piece and what else?
So it includes, so it's whatever is not included in this. So it includes that
And the phi less part.
and this. Because the part of it that depends only on phi less doesn't care whether you do this integral or not, right? So the integral matters only insofar as phi less and phi bigger are connected to each other. Okay? Good. So now let's actually do that. So of course first we have to do this. Right? And we ask ourselves, what will we get when we do that? Okay. So you know that when I take the average of this guy, it's going to be the average, so let's write down what is v. Okay, so v looks like lambda over 4 with a minus sign, right? The integral d to the dx of 4 phi less cubed phi bigger plus 6 phi less squared phi bigger squared plus 4 phi less phi bigger cubed plus 5 bigger to the 4. That's what it looks like, right? Now I want to take the average of this in the quadratic theory of phi bigger, right, or phi fast. So let's remember what the averages are, right? So clearly, phi fast of x, phi fast of x prime, what is it going to be? Well, we know what the quadratic theory is. And remember, we did Gaussian integrals last time, right? Or the time before that, or sometime, right? We know what the correlation function is. It's really just the inverse of this. Okay, so it's basically going to be the integral of lambda times 1 minus dl to lambda d to the dk over 2 pi to the d times e to the I, okay, k dot x minus x prime divided by lambda squared plus n squared. Right? That's where it's going. Okay? So let's work it out. What are the terms that will actually have an average? Anything with an odd number of phi fast will not survive, right? So you have to only look at terms that have an even number of phi fasts. So it has to be either this guy or that guy. Okay? This guy will give me something. Okay, will give me something, but that something is independent of phi slope. The whole purpose of doing this is to look at terms that depend on phi slope and use them to renormalize my slope effective action. Okay? So I say we just ignore this. So we've got only one term left, and that's this one.
Why, sir, why did you ignore that term?
Why did I ignore that term? Because the point of doing this is to look at the effect of this fast degrees of freedom on the slow degrees of freedom.
Okay. And there is
This
no-
doesn't contain any slow degrees of freedom, so it won't have any effect on it.
It will just factor out and.
It will create a constant in the free energy.
Okay.
Okay, it will change the free energy. Remember when we did the one-dimensional Ising model, right? There was a similar thing there. Like when we took t squared,
Yes.
if you wanted to write it as t of 2 times k tilde, there was an extra constant that separated out. And I said that was the free energy of those sites that you are integrating. It's very similar to that. That's what this is.
Okay.
Okay? So, right? Everybody happy with this? Okay. So we do it, and this sign is minus. So the only term that survives out of this, so e to the average b is going to look like e to the minus lambda over 4. And remember, it's phi greater squared at the same point. Okay, it's the same point. That's here. So basically, it's just going to look like, so that's integral dx, right? There's still a phi less squared of x. Nothing is happening to it because we're not integrating it out. So now, this is going to look like integral d to the dk over 2 pi to the d. Lambda times 1 minus dl to lambda, right? 1 over lambda squared plus m squared. Right, that's the effect. Okay. So now, this integral can be done, okay? Especially if dl is very small, which it is. dl is infinitesimal. So what I'm going to do is I'm going to define a number called s d minus 1. It's connected to the area of the d minus 1 dimensional sphere. Okay? But it's got a 2 pi and so on in it. Okay, so let me say the following way. It's d omega d minus 1 over 2 pi to the d. Okay? That's what it is. Alright? Good? So, this thing doesn't depend on angle. Right? So I can basically integrate out the angles. And then the actual integral itself, right, what is it going to be? Let's just count dimensions. So I'm going to write down some answer, and then we will see that it has to be correct. So it's proportional to dl, right? Certainly also proportional to 1 over lambda squared plus m squared. Right? And then it's going to have the s d minus 1, but it's also got to have a lambda to the power of d. Just look at the dimension. Right? You've got to be there. No other choice. Okay? Good.
Actually, the other factor is something like the surface of the sphere that we are
D-dimensional, D minus 1 dimensional sphere. That's
Yes,
correct.
yes, and the thickness that is.
Thickness is
Precisely. The thickness is dl.
Lambda into
It's lambda times dl.
that lambda.
But then, it's all included. Okay? I won't say anything to you because you helped me out. Okay? So, alright. So that's what it is, right? Good. So now, let's ask ourselves what effect this has on the m squared term. Because this is going to go back and renormalize the m squared term. Because it's a phi squared. Right? So, let me say then that m prime squared is going to be equal to m squared times 1 plus dl squared, right? This came from the 3-level scale that we already did. And now there's going to be this back reaction of the lambda term onto the m squared term comes to the minus sign in the effective action, right? Because it's e to the minus s, right? So this comes to the positive sign, whatever is happening here. Okay?
Is
So,
that all that we have here?
There's also a 6 here, by the way.
Yeah, and is there another D?
This is 6. Sorry, a D.
Yes. I'm sorry, but.
What D? Which D? Dimension D? No.
So
How can
it's,
there be a dimension?
it's a lambda D minus lambda into 1 plus D DL to the whole to the D, right?
What?
He's
No, no, the thickness of the shell is lambda times dr.
No, when I'm integrating the radial part.
The radial part is the infinitesimal part. So I've done the area integral. The area integral gives me a lambda to the d minus 1
Correct.
times a lambda dr. So that's the lambda to the d. That's what he was saying.
Actually, it's something like that. That we have, if we just raise that lambda to the power d into 1 minus dl to the power d minus lambda to the power d, that just factored out the d. Possibly.
What? Come on. That's ridiculous. Look. The thickness is the only infinitesimal dimension. Okay?
Okay,
When I do the
okay.
angular integral, there's no thickness involved.
Understood.
No, I'm not talking about the angular integral actually. So after the angular integral,
This is correct. This is actually correct. But yeah, anyway, I shouldn't stop. Yes, go ahead.
I was just saying that after the doing the angular integral, I have a k to the d minus 1 dk integral.
Yeah.
I'm saying that gives me a lambda to the d, capital lambda to the d minus that other thing, right?
Which
But
other?
the lower limits is lambda times 1 minus dl whole to the d.
Yeah.
But
Not
1
to the
minus
D, that's the point, not to the D. It's not to the D.
I'm missing something.
Okay?
No, I'll just think.
Yeah, it's all included inside SD minus 1. The thickness is the only infinitesimal dimension. So 1 minus DL can only appear once. Cannot appear more than once. Okay? Good, so that's what it is. Alright. So then, let's see what happens here. So I have a plus, okay? Now, I have 3 by 2 lambda, right? A 6 and a 4. And then I have this SD minus 1. And then I have lambda to the power d divided by lambda squared plus m squared. Okay, that's what I have. That's the renormalization of m squared times dl, sorry. Okay, good. Now I don't like all these powers of lambda because you see the reason these powers of lambda are appearing is because the couplings that we have are dimension full. We want to make them dimensionless. So let's do it. Okay, how do we do it? We use the engineering dimension or the naive dimension of these fields. So we say that m, so let me define m squared is m tilde squared times lambda squared. Okay, because the dimension of m squared was 2. Right? So if I put this here, that will take care of the naive dimension of m squared, leaving behind something dimensionless. Okay? Good. Similarly, with lambda, I will define it as some lambda tilde times lambda to the 4 minus d. Again, the naive dimension of lambda was 4 minus d, and this will deal with that. If I have done everything correctly, then this entire equation should become dimensionless. Okay? So let's just check that. Okay. So I have, oh, I'm sorry, I think I did something wrong here. This was, right? It was a determined effective action of the m squared. Alright, so let me get rid of that 2 and say the following thing. So here's m tilde squared lambda squared is prime squared. M tilde squared lambda squared 1 plus 2 dl, right? Plus 3 lambda tilde lambda to the d minus 4, sorry, 4 minus d, right? And then I have lambda to the d SD minus 1 dl over lambda squared times 1 plus m tilde squared. Agree with that? Alright? So now I can cancel lambda squares from everywhere. That's gone, and this entire power is lambda squared. Right? So I get rid of it. That. Okay? Good. So this tells me that if I write a differential equation for the flow of this m tilde squared, the right hand side of this is always called the beta function of m tilde squared. Okay? What does that look like? It looks like 2 times m tilde squared plus 3 lambda tilde SD minus 1 okay? Good enough? Alright? Any questions? Because now we're doing an actual calculation, and in the end we're going to get a new fixed point and we're going to get some new critical edge points.
So this difference of the shells is lambda and lambda 1 minus dl. So this differential is a dimensionless quantity, right?
Yeah.
How do you interpret it in terms of this flow equation? Like what is L for you?
L is basically like log of lambda prime over lambda or something. Right?
D of log.
Yeah, something like D of lambda. Right?
But in all your calculation that went through, never came out like how to just work. Like this in this rate equation, what is the physical notion for L? It never came through the.
L is the scale that we have rescaled. Okay? So in other words, remember what we did with x, right? Remember we said x prime was x times 1 plus dl. Right? If you continuously do this, eventually you know that this is going to become x e to the l, right? So that's the amount by which you rescale. Okay, so you start with your bare effective theory if you want. Okay, at L equals 0, and then you start rescaling it, and by the time you've reached L, it's rescaled in physical units by e to the l. Okay, that's what the meaning of L is. Okay, does it make sense?
So experimentally, do we have some control over L?
No, it's not an experimental object at all. So the point is that this is something we are doing theoretically. We're integrating out the fast degrees of freedom. You don't do that. When you do an experiment, you just measure whatever the system tells you, right? You're not integrating anything out. This is our way to describe the system. Okay? A purely theoretical concept. But in the end, we'll be able to relate it to some measurable points. Okay? Another question. Yeah.
So we can always, so this description should hold at some low energies, okay, since we have integrated at high degrees of freedom. So
Right.
in that sense, so that is also the interpretation of this energy.
So the larger the L,
Yeah.
the lower the energy scale you're at.
Yeah.
Or the longer the distance scale you're at.
Yeah.
That's right. Yeah, that's right. Okay? Good? Alright. So that is one equation. This is one renormalization group equation. Now we want the other one. Okay? Now the other one of course has to be the lambda. Right? So let's do the lambda. So let's see what happens there. Actually, I don't know if I have the time to do it. Can I stop and do it next time? Because it's going to take a little while. Okay, that's so I don't want to like do it when you guys are tired. Okay, let me just tell you what it is, and then we'll actually do it next time.
And so the higher order terms here.
Correct. So the next term, so we already dealt with this. So now we're going to start dealing with this. Okay, and here, again, it's going to be the same player as this guy. Okay, this guy is going to come in, and it's going to have a phi less squared, phi bigger squared, and 2 powers of that. Okay, so in the end, you're going to have 4 powers of phi slope. And that's what you want in order to normalize the 4-point coupling, right? And so that's what you want. So this is the guy that's going to play a big role. Now you might imagine that I could also do this, right? But you actually cannot. Okay, the reason is that what you're really focusing upon is low momenta for these guys. Okay, so these guys, we should really think of them as being near the center of this ball of lambda. Okay? If they're near the center of the ball of lambda, there's no way you can even have this. Because remember, there's momentum conservation. Okay? So whatever effect this guy has, we'll only have it near the edges of this ball. Okay? So in fact, this term is not important. It's only this term that is important still. So we're going to take 2 powers of that term, and we're going to take the connected correlation function of 2 powers of that. And that will tell us how lambda renormalizes.
So this 6, 5, that piece and that piece can correct.
This one here,
The second piece and the fourth piece.
this one and that
That
one.
will correct phi square.
That can correct phi squared.
Two
That's
piece.
true. That can correct phi squared. Absolutely. Now, it turns out, what is it not?
No, which can correct phi square? Sorry.
So the thing is that what she's saying is that if I take this guy and that guy, it can certainly correct phi squared. You're right. You're right. I'm wondering whether that's important or it's not important.
No, it give rise to phi 6.
No.
So it will correct
This one, you have to remember, you have to contract, you have to average over all the phi fast. So what is left behind is just a phi squared. So it can certainly correct the mass term, okay? I'll go back and think about it. I think it's not important for some reason, but maybe it is, okay? So we can think about that. And
lambda squared.
that'll be a lambda squared term. I believe it's not important, but let's calculate it anyway, okay?
There are two
And then there is so at this order, there's really nothing else, right? There's nothing else. You can also imagine the following situation, right? You can imagine 2 powers of this. It can create a phi 6 coupling, okay? And that would look like the following diagram, right? Okay, this is a phi fast, and these are all slows. Right? You could imagine that. But again, it's not important. Why? Because think about low momenta for all these guys. They're near the center of the ball. Right? So therefore, this guy cannot even exist. So another way of thinking about it is the following. So remember, you have these couplings, right? Now, what I'm doing when I expand in momentum space, I'm looking at something. So let's take a phi 4 coupling, right? I could have the following situation. I have d to the d k1, d to the d k2, d to the d k3, right? And I could have phi of k1, phi of k2, phi of k3, and phi of minus sigma ki, right? This conserves momentum. But I could also have, so I put a constant out there, right? But instead of a constant, I could have lambda, I could maybe expand it in momentum, powers of momentum, right? It's a scalar. So I can do something like, k squared lambda prime of 0 plus k to the 4th lambda double prime of 0 and so on. I could do that. Now the point is that each of these guys is more irrelevant than this guy, because you have added 2 dimensions here. right? So whenever we try to compute the lambda that we are normalizing, we're really implicitly thinking about this guy, lambda of 0. That's what we're actually computing, okay? And when we do this, you find a lambda that's near the edges of the ball, but it's not present at 0. Okay, so this guy doesn't actually create a U6 at 0 moment.
But we can manage to calculate this, right?
Of course you can calculate it, yeah.
Then we should see that the U6 is shrinking.
The U6 will always shrink anyway, but this is not just a U6. I'm saying this is some U6 that exists only near the boundaries of the ball.
So we take the A going external momentum going to 0 limit.
Correct.
And in that limit these diagrams draw.
That's right. That's right.
And what about the two loop diagram? That is suppressed by lambda square. Is it?
Which two loops?
So there is this 6 and so pi
This one
square,
here.
pi square and pi 4. Yes.
Okay, so this guy will look like there's that, and then there are 2 of these guys coming out, and then there's 4 of these guys, right?
So there is a two loop.
So you can do this, and that, and that.
Right.
Yeah, you can do it. It's order lambda square.
Lambda square. So
It's order lambda square. I think I know why it's not important, but we'll do it, and we will show you it's not important.
but we are anyways keeping till order lambda. Is it? Or
No. We're actually going to keep the second order in everything. Okay, lambda and f. Okay? Because you will need it in order to get the correct critical exponent, you actually need to keep second order in both lambda and f.